Selvi Manoharan, and I'm the founder of Bubbles and KK and also founder of Curious and Connected. So these are very new startups, and these startups are basically focused on research in robotics, quantum information science, and and related technologies like spintronics. And one of the main focus of this research is leveraging the microgravity environment for experiments for the advancement of the technologies. So today I'm going to talk about spin qubits. Spin qubits are a type of quantum qubit and have gained significant attention due to their potential for scalability and long coherence times. And let's talk about spin qubits. So basically, to understand the spin qubits, we need to talk about principles of quantum computing. So when we talk about the principles of quantum computing, quantum bits, we need to know about qubits. As we all know, qubits are just like how traditional computers use 0 and 1 to represent information. Quantum computers use qubits in superposition, 0 and 1 simultaneously, and superposition enables parallel processing and more efficient problem solving. And the next principle would be entanglement, a fundamental property of quantum mechanics. Entangled qubits have correlated states regardless of distance, enables powerful parallel computations in quantum computers. And the next principle would be coherence. Coherence refers to the stability and preservation of qubit quantum states. So coherence time is crucial for accurate and reliable quantum computations. Quantum dot spin qubits show promise in achieving long coherence times. So what are quantum dot spin qubits? Basically, quantum dot spin qubits are spin qubits that are made of quantum dots. And spin qubits can be made of many different materials, superconducting materials, and a lot of, we do have a whole list of materials that could be used for manufacturing quantum dots, and that are potential research candidates. But currently I'm going to talk about spin qubits that are made of quantum dots. Quantum dots are basically nanoscale structures confining electrons or holes in a small region. They exhibit discrete energy levels, allowing manipulation of single or few electrons. They provide well-controlled environment for qubit manipulation. And spin qubits, basically they exploit the intrinsic spin property of electrons for representing quantum information. They utilize the up and down states of electron spins, 0 and 1 respectively, and quantum dot spin qubits use trapped electrons as qubits. And there are a lot of advantages of using quantum dots for spin qubits. Scalability. Quantum dots arranged in an array enable scalable quantum computing. Integration of multiple quantum dots add more qubits, increasing computational power. And they're crucial for tackling complex problems requiring significant computational resources. And the next main advantages for using quantum dots as spin qubits would be high fidelity. Quantum dots provide a controlled environment for precise spin qubit manipulation, and they have minimized environmental noise and unwanted interactions, which could lead to high fidelity operations. And they ensure accurate and reliable quantum computations, reducing errors and improving performance. And long coherence times, again, quantum dots, they demonstrate promisingly long coherence time when compared to other materials, similar materials, especially silicon quantum dots. And there are other materials too, but that is not in the scope of this presentation, because this presentation is basically focused on talking about spin qubits. I'm not focusing a lot on talking about advanced materials. And long coherence times, basically they allow more for quantum operations and reduce decoherence efforts. integration with existing technologies. Quantum dots can be seamlessly integrated with existing semiconductor technologies, and they leverage established fabrication techniques, enabling incorporation into larger quantum computing systems, and accelerates development and commercialization, making quantum computing accessible to researchers and industries. Fabrication and control of quantum dot spin qubits. Again, these are some of the main focus of our research. The fabrication process, here I've listed the very basic ones, but the very basic steps, but again, because this presentation is only for 20 minutes, I couldn't go much into detail. So advanced nanofabrication techniques, fabrication of quantum dot spin qubits requires advanced nanofabrication techniques such as electron beam lithography, molecular beam epitaxy. Those are the two main ones. And formation of quantum dots. Nanoscale quantum dots are formed by carefully confining electrons or holes in a controlled manner, typically in semiconductor materials. And quantum dot design. Precise control of quantum dot parameters such as size, shape, and composition is essential to qubits with desired properties. Control methods. Electrostatic gates. Electrostatic gates are used to manipulate the electron spin states within the quantum dot. Magnetic fields. External magnetic fields are applied to control the energy levels and spin states of the electrons. Spin resonance technologies. Spin resonance techniques such as electron spin resonance and nuclear magnetic resonance are employed to read and manipulate the spin states of the qubits. Coherent control techniques such as laser pulses or microwave pulses are used to perform operations on qubits such as initialization, manipulation, and measurement. Precision and reproducibility. Precise quantum dot placement. Advanced fabrication techniques enable precise placement of quantum dots, ensuring reproducibility and uniformity across multiple qubits. Uniformity of quantum dots. Achieving uniformity in quantum dot properties such as size and composition is crucial to ensure consistent qubit behavior, and error correction. Error correction techniques are employed to mitigate the impact of imperfections and noise, ensuring the reliability of quantum computations. And another main focus of this research would be advancement in materials and device architectures for quantum dot spin qubits. So here I've listed a very few of the advanced materials such as isotopically purified silicon. The advantages are coherence time extension. Isotopically purified silicon enriched with 28 silicon strands. The coherence time of spin qubits reduced decoherence, minimizing 29 silicon and 30 silicon isotopes, mitigates magnetic noise and nuclear spin effects, resulting in longer coherence times, and improved quantum operations. Extended coherence time enhances the accuracy and reliability of quantum operations. And the next would be topological insulators, potential protection. That's again this would be the next focus of our research. There are like a lot of research going on topological insulators. Some of the examples are bismuth telluride, Vi2, T3, and can protect qubit coherence and increase robustness against environmental noise. And device architecture, this would be the next step of the research. A few of the examples are hybrid systems, 3D architectures. Basically hybrid systems, they provide enhanced stability, integrating quantum dots qubits with superconducting circuits, improves quantum computing system scalability, and improved control. Superconducting circuits offer precise electrical control and rapid qubit operations, enhancing qubit manipulation and readout. And hybrid systems combining quantum dots and superconducting circuits enables exploration of hybrid quantum systems for advanced quantum information processing. And when it comes to 3D architectures, increased qubit density, three-dimensional architectures allow higher qubit density and improved scalability, efficient qubit interactions, vertical stacking of quantum dot facilities, compact arrangements, and efficient qubit interactions, reducing crosstalk between qubits. And potential applications of quantum dot spin qubits. Quantum dot spin qubits have diverse potential applications in quantum computing and other fields. They enable the simulation of complex quantum systems, leading to advancements in quantum chemistry, material science, and condensed matter physics. Spin qubits offer the ability to solve large optimization problems more efficiently, impacting various sectors such as logistics, finance, and cryptography. Their potential in materials and drug development can accelerate the discovery of new materials with desirable properties and aid in the optimization of molecular structures for drug design. The exploration and realization of these applications will unlock the full potential of quantum dot spin qubits and revolutionizing industries and pushing the boundaries of scientific discovery. So currently I've proposed a few NLRA to the ISS National Lab for experimenting with quantum dot spin qubits in the ISS, and I'm going to talk about that now. So experiments on ISS basically provides valuable insights. We have various experiments with respect to coherence, initialization, readout, interactions, and material experiments that contribute to quantum computing advancements. And coherence experiments, basically they investigate the duration for which the qubits can maintain their quantum state. So the ISS can minimize decoherence by isolating qubits from environmental disturbances. Longer coherence times are crucial for accurate quantum computing operations. And initialization experiments explore techniques to reliably initialize qubits into known states. ISS experiments can compare methods like optical pumping, electrical control, and qubit interactions. Precise initialization is essential for accurate quantum computing operations. And readout experiments aim to accurately measure the quantum state of qubits. ISS experiments study different readout techniques like short sensing, spin readout, photon detection, etc. Enhanced readout techniques improve the fidelity of quantum computing operations. So interactions and coupling experiments. Interactions and coupling experiments investigate the behavior of multiple qubits. ISS experiments focus on studying the entanglement and controllable interactions between qubits. And scalable and controllable interactions are crucial for complex quantum computations. Material and manufacturing experiments, they explore novel materials and fabrication processes. ISS experiments leverage microgravity to test materials and manufacturing techniques. Advancements in materials and manufacturing enhance qubit performance and reliability. So here are some examples that we have lined up for the ISS, like characterization of spin qubits and microgravity. This is the objective would be to characterize the behavior and properties of spin qubits in a microgravity environment. This would involve spin qubit platform and sensors, control systems, measurement devices, and data analysis. And the next one would be coherence time enhancement strategies. The objective would be to explore strategies to enhance the coherence time of spin qubits in microgravity. And and uh, and uh, and then the data analysis could also leverage the data from the previous experiment and compare the coherence time. And another experiment would be quantum error correction and fault tolerance. Here the objective would be to explore error correction and fault tolerance techniques in microgravity. Again, the data analysis could include assessing the effectiveness of the error correction techniques. Again, we have a lot of techniques lined up there. So this is basically a very iterative research that it's like a chain reaction. One research, the data from one research could be used in the next research, and so it gives way to a lot of iterative researchers, and a very useful data set that could be used in machine learning and iterative studies and refinements. So the approach would be to design successive experiments building upon the previous finding and refine understanding of spin qubits and microgravity. So some of the iterative studies could include exploring different spin qubit implementations, testing novel materials and fabrication techniques, refining control and measurement protocols. So the goal of advancing quantum technologies in microgravity is to advance the understanding and optimize the performance for practical quantum technologies, and the impact would be to leverage unique advantages and pave the way for development of reliable quantum technologies. And successive experiments and iterative studies propel quantum computing in microgravity, and they open doors to new applications and possibilities in the realm of quantum information processing. So if you have any questions, please feel free to email me. I could get you a very detailed answer. But I'm very welcome to take the questions now, but I may not have the answer because the theory is huge, and I may need to refer.
Do we have any questions today? Yes.
So
Yeah.
other than just putting the qubits in microgravity, right? Or so getting rid of gravity on Earth, that is beneficial. Are there any other factors on the ISS that kind of help in terms of qubits, in terms of quantum computing and stuff?
Yeah, basically this experiment or the research also focuses on synthesizing the quantum dots itself, and also testing the behavior of spin qubits that's made of different materials. Basically, we need to understand the behavior of spin qubits, the quantum systems itself in microgravity, because in the future, with space exploration, a lot of quantum systems, like from quantum metrology to quantum sensing, a lot of quantum system technologies would be used in space-based technologies, like even space-based explorations and settlements. So this builds the quantum system for that.
Any other questions today?